According to the National Fire Protection Association 72, low voltage and fire alarm cables should not share the same raceway. This is because low voltage and fire alarm cables have different electrical characteristics, and sharing the same raceway could create a safety hazard. The different electrical characteristics pose risks such as electromagnetic interference, where the low voltage cables could induce noise or disrupt the signals in the fire alarm cables, potentially leading to false alarms or failure of the fire alarm system to operate correctly. Physical damage is another concern. If a fault occurs in one of the systems, it could damage the other system, leading to compromised performance or even complete failure. Additionally, the different voltage levels present in the same raceway could pose a safety hazard to anyone working on the electrical system, increasing the risk of electric shock. Furthermore, the installation described uses a 24-volt relay coil connected improperly, and this improper wiring can create multiple hazards. The 24-volt relay coil should be connected to its designated 24-volt power source, not a 110-volt power source. Connecting a 24-volt device to a 110-volt supply can cause immediate damage to the relay, potentially leading to overheating, fire, and failure of the lighting circuit. When the 110-volt power source should be connected to the load side of the relay, this allows the relay to switch the 110-volt power to the lights on and off, but only when the relay is properly energized by the 24-volt control circuit. The relay acts as a switch controlled by the low voltage circuit to safely manage the high voltage lighting circuit. To ensure safety and correct operation, I would recommend that you consult with a qualified electrician to correct the wiring and ensure that the system is safe and compliant with the electrical codes and standards. The electrician will start by disconnecting the improperly wired relay and assessing the extent of any damage. They will replace any damaged components and rewire the relay correctly, ensuring that the 24-volt coil is connected to a 24-volt power supply and that the 110-volt power source is connected to the load side of the relay. The electrician will verify that all wiring is correctly sized and protected, in accordance with electrical codes. They will also test the operation of the three-way switches and the lighting circuit to ensure that everything is functioning as intended. More detailed explanation on the problem: the National Electrical Code, or NEC, provides guidelines for the installation of electrical systems. Firstly, NEC Section 300.3 code generally requires that conductors of different electrical systems be kept separate unless specifically permitted otherwise. Secondly, NEC Section 725.136I provides specific requirements for the separation of Class 1, Class 2, and Class 3 circuits, which often include low-voltage circuits. This section mandates that these circuits must be separated from power circuits unless specific conditions are met, such as being installed in a raceway or having adequate insulation. Thirdly, the NEC addresses fire alarm systems in Article 760. This article requires that fire alarm circuits be installed in a manner that minimizes the risk of damage and ensures reliable operation. Sharing a raceway with other electrical systems can increase the risk of interference or damage, thus violating the intent of Article 760. There are several hazards in sharing raceways. Firstly, electromagnetic interference may occur. Low-voltage circuits can generate electromagnetic interference, which can disrupt the signals in fire alarm circuits, leading to false alarms or system malfunctions. Secondly, physical damage is possible. A fault in one system can cause physical damage to the other system within the same raceway, compromising the integrity and reliability of both systems. Thirdly, voltage induction can be a problem. If a high-voltage wire shorts to the conduit, it can induce a voltage in the low-voltage wiring, causing damage or creating a safety hazard. Fourthly, non-compliance with codes can lead to more problems. Sharing raceways between fire alarm and other electrical systems can violate the NEC and NFPA 72, leading to potential fines, insurance issues, and increased liability in case of an incident. Here is the explanation of how to correct the wiring of the three-way switches. Firstly, identify the power source. Determine the source of the 110-volt power that will be used to supply the lights. Secondly, connect the power to the relay. Connect the 110-volt power source to the normally open contact of the relay. This will allow the relay to control the power to the lights. Thirdly, connect the lights to the relay. Connect the lights to the output of the relay so that when the relay is activated, it will supply power to the lights. Fourthly, wire the 24-volt coil. Connect the 24-volt power source to the coil of the relay. This will energize the relay and allow it to switch the 110-volt power to the lights. Fifthly, install the three-way switches. Wire the three-way switches so that they control the 24-volt power to the relay coil. This will allow you to turn the lights on and off from multiple locations. Sixthly, test the system. Once the wiring is complete, test the system to ensure that the lights turn on and off correctly from all switch locations. More on the correct wiring of three-way switches. Firstly, each three-way switch has 3 terminals, a common terminal, and 2 traveler terminals. Secondly, the common terminal of the first three-way switch is connected to the power source, in this case, the 24-volt power supply for the relay coil. Thirdly, the 2 traveler terminals of the first three-way switch are connected to the 2 traveler terminals of the second three-way switch. Fourthly, the common terminal of the second three-way switch is connected to the relay coil. Fifthly, when the position of either three-way switch is changed, it alters the path of the current, either completing or breaking the circuit to the relay coil, thereby turning the lights on or off. Some information about fire alarm cable is firstly, fire alarm cable is specifically designed and constructed to meet stringent requirements for fire resistance, signal integrity, and overall reliability in fire alarm systems. Secondly, these cables must maintain their functionality during a fire event to ensure that alarm signals can be transmitted and received, even under extreme conditions. Thirdly, fire alarm cables are typically constructed with specialized insulation materials that are capable of withstanding high temperatures without melting or degrading. Fourthly, the conductors are often made of materials that resist corrosion and maintain conductivity over extended periods. Fifthly, fire alarm cables are designed to minimize electromagnetic interference, which can disrupt the sensitive signals used in fire alarm systems. Sixthly, fire alarm cable is tested and certified to meet industry standards such as those set by Underwriters Laboratories (AL) and the National Fire Protection Association (NFPA). Reasons for consulting a qualified electrician are firstly, safety compliance. A qualified electrician will ensure that all wiring and installations comply with the NEC and local electrical codes. Secondly, proper installation. An electrician will have the knowledge and experience to properly install and wire the electrical system, ensuring that it operates safely and reliably. Thirdly, troubleshooting expertise. An electrician can quickly diagnose and repair any electrical problems, minimizing downtime and potential hazards. Fourthly, long-term reliability. Proper installation and maintenance by a qualified electrician can help ensure the long-term reliability of the electrical system, reducing the risk of future problems. Fifthly, insurance requirements. Many insurance companies require that electrical work be performed by a licensed electrician to maintain coverage. Now some notes on fire alarm system requirements. Firstly, the National Fire Protection Association, NFPA, sets standards for fire alarm systems through NFPA 72, the National Fire Alarm and Signaling Code. Secondly, this code provides detailed requirements for the installation, testing, and maintenance of fire alarm systems. Thirdly, fire alarm systems must be designed to provide early warning of a fire, and to reliably transmit alarm signals to the appropriate authorities. Fourthly, the components of a fire alarm system, including detectors, control panels, and notification appliances, must be listed and approved for their intended use. Fifthly, regular inspections and testing are required to ensure that the fire alarm system is functioning correctly. Sixthly, any modifications or repairs to the fire alarm system must be performed by qualified personnel. Here is some information on the NEC and electrical safety. Firstly, the National Electrical Code, NEC, is a set of standards developed by the National Fire Protection Association, NFPA, to ensure the safe installation of electrical wiring and equipment. Secondly, the NEC is updated every 3 years to reflect changes in technology and industry best practices. Thirdly, compliance with the NEC is essential for preventing electrical hazards such as fires, shocks, and electrocutions. Fourthly, the NEC covers a wide range of electrical topics, including wiring methods, overcurrent protection, grounding, and equipment installation. Fifthly, local jurisdictions often adopt and enforce the NEC, making it a legal requirement for electrical installations. Sixthly, it is important to consult the latest edition of the NEC and to seek the advice of a qualified electrician to ensure compliance with all applicable requirements. A deep dive into the correct wiring configurations should start with, firstly, understanding three-way switch circuits. In a three-way switch circuit, there are two three-way switches and the electrical device, in this case, the lights. Secondly, each three-way switch has a common terminal and two traveler terminals. Thirdly, the power source is connected to the common terminal of one of the three-way switches. Fourthly, the two traveler terminals on the first switch are connected to the two traveler terminals on the second switch. Fifthly, the common terminal on the second switch is connected to the electrical device, the lights. Sixthly, the neutral wire from the power source is also connected to the electrical device to complete the circuit. Seventhly, the key to a three-way switch is that the internal switch mechanism connects the common terminal to one of the two traveler terminals. This allows the current to flow in different paths depending on the position of the switches. Eighthly, when both switches are set to allow current to flow through the traveler wires, the light is on. When either switch is flipped to break the connection through the traveler wires, the light is off. Now, let's discuss safety precautions for electrical work. Firstly, always turn off the power before working on any electrical circuit. Use a circuit tester to ensure that the power is off. Secondly, wear appropriate personal protective equipment, including safety glasses and insulated gloves. Thirdly, never work on electrical equipment in wet or damp conditions. Fourthly, use tools with insulated handles. Fifthly, follow all applicable electrical codes and safety standards. Sixthly, if you are not comfortable working on electrical circuits, hire a qualified electrician. Seventhly, double-check all connections to ensure they are tight and secure. Eighthly, keep a fire extinguisher nearby in case of electrical fire. Ninthly, be aware of your surroundings and avoid distractions while working on electrical circuits. Tenthly, if you are working on a ladder, make sure it is stable and secure. Reasons to avoid unapproved modifications are, firstly, safety hazards. Unapproved modifications can create safety hazards such as electrical shock, fire, and equipment failure. Secondly, code violations. Unapproved modifications often violate electrical codes and standards, leading to potential fines and legal issues. Thirdly, insurance implications. Unapproved modifications can void insurance coverage in the event of a claim. Fourthly, equipment damage. Unapproved modifications can damage electrical equipment, leading to costly repairs or replacement. Fifthly, system reliability. Unapproved modifications can compromise the reliability of the electrical system, leading to unexpected downtime and disruptions. Sixthly, liability concerns. Property owners and managers can be held liable for injuries or damages resulting from unapproved electrical modifications. Discussing the relay operation in detail. Firstly, the purpose of a relay is to use a low voltage signal to control a higher voltage circuit. Secondly, the relay consists of an electromagnetic coil and a set of contacts. Thirdly, when the coil is energized, it creates a magnetic field that attracts a movable armature. Fourthly, the movement of the armature opens or closes the contacts, thereby controlling the flow of current in the higher voltage circuit. Fifthly, relays are commonly used to switch lighting circuits, control motors, and operate other electrical devices. Sixthly, the relay coil is typically rated for a specific voltage, such as 24 volts, and should be connected to a power source of the same voltage. Seventhly, the contacts of the relay are rated for a maximum voltage and current, and should not be exceeded. Eighthly, there are different types of relay contacts, including normally open, no, and normally closed, NC. Ninthly, a normally open contact is open when the relay is not energized and closes when the relay is energized. Tenthly, a normally closed contact is closed when the relay is not energized and opens when the relay is energized. Examining common wiring mistakes. Firstly, incorrect wiring of three-way switches. This can cause the lights to not turn on or off correctly from all switch locations. Secondly, overloading circuits. This can cause circuit breakers to trip or fuses to blow. Thirdly, using undersized wires. This can cause the wires to overheat and potentially start a fire. Fourthly, improper grounding. This can create a shock hazard. Fifthly, failing to properly secure connections. This can cause loose connections and potential electrical problems. Sixthly, neglecting to label circuits. This can make it difficult to troubleshoot electrical problems in the future. Seventhly, ignoring electrical codes and standards. This can lead to unsafe installations and potential legal issues. Eighthly, working on live circuits. This can result in electrical shock or electrocution. Understanding insulation requirements is firstly, electrical insulation is a non-conductive material used to protect wires and cables from electrical leakage, short circuits, and contact with other objects. Secondly, insulation is rated based on its ability to withstand voltage and temperature. Thirdly, different types of insulation are used for different applications depending on the voltage, temperature, and environmental conditions. Fourthly, common types of insulation include thermoplastic, thermoset, and rubber. Fifthly, the thickness of the insulation is determined by the voltage rating of the wire or cable. Sixthly, damaged or deteriorated insulation can create a safety hazard and should be repaired or replaced. Seventhly, when selecting insulation, it is important to consider the environmental conditions such as temperature, moisture, and exposure to chemicals. Eighthly, proper installation and maintenance of insulation are essential for ensuring the safety and reliability of electrical systems. Delving into grounding and bonding. Firstly, grounding and bonding are essential for electrical safety. Secondly, grounding provides a path for fault current to flow back to the source, causing the circuit breaker to trip or the fuse to blow, thereby preventing electrical shock. Thirdly, bonding connects all metal parts of an electrical system together to create a low impedance path for fault current. Fourthly, the grounding electrode system consists of a grounding electrode, such as a ground rod or metal water pipe, and a grounding electrode conductor. Fifthly, the grounding electrode conductor connects the grounding electrode to the neutral bus in the electrical panel. Sixthly, equipment grounding conductors connect the metal parts of electrical equipment to the grounding system. Seventhly, proper grounding and bonding can prevent electrical shock, minimize the risk of fire, and protect sensitive electronic equipment from damage. Eighthly, grounding and bonding should be inspected and tested regularly to ensure that they are functioning correctly.